So in this Chapter 16 video cast, we'll finish up with sections 16.3 and 4 and move into section 16.5. And we'll look at a ranking scale, one that tells us how strong acids and bases are based on how much H plus and OH minus they contain. And these are called a P scale, called the pH and the POH. So just a tiny bit of chemistry in your everyday life. Again, in this video cast, we've been talking about amino acids and how they can act as bases, proton acceptors, and acids both at the same time, even though they're in the same molecule. Well, depending on how many H's these give up, or how many H's these accept, on the macroscopic scale, we can say how acidic or how basic these things act. Most of the time, glycine in 25 degrees Celsius solution has a pH of about 6, meaning that on the pH scale, which goes from 0 or so all the way up to a little more than 14, the amino acids, with 7 being neutral of course, the amino acids act a little bit acidic, so they're right over here, meaning that they will give up hydrogens a little bit more readily than they will gain hydrogens. So let's jump right in and let's look at this ranking scale. This ranking scale, of course, is called the pH scale, and the pH scale is dependent upon how much H plus ion there is in solution. And since the H plus ion concentration in solution is usually small, something in the order of times 10 to the negative 2, 3, 4, 5, 6, and not just a handy number like 5, it's helpful to express this in a logarithmic scale. And so the pH of a solution is defined as the negative logarithm of the hydrogen or hydronium ion concentration. pH is equal to negative log of H plus. And at 25 degrees Celsius, water has an H plus ion concentration of 1 times 10 to the negative 7th. And so if we wanted to know the pH of water at 25 degrees Celsius, we'd take the negative log of 1 times 10 to the negative 7th, then this would be equal to 7, and that's where neutral comes from, or that 7 is like not acidic, not basic, it's right in the middle. Also, if we wanted to know the OH minus ion concentration and then describe it in terms of a P scale, the POH is equal to the negative log of the OH minus ion concentration, and it turns out for water, OH minus concentration is also 1 times 10 to the negative 7th, and so you take the negative log of 1 times 10 to the negative 7th again, and that would be 7 as well. So we have two P scales now, and we have the OH minus concentration and the H plus ion concentration to describe something that is acidic or basic. So let's put it all together. And we put it all together in what's called a pH square. And if you take your periodic table out, you can turn to this page right here and pause the video now so then you can take a look at this. Make sure you've got yours out in front of you. I'll pause for about 5 seconds and wait for everybody to have this. You can see that we have a relationship between pH and H plus ion concentration, and if you want to find the pH from the H plus, you take the negative log of the H plus ion concentration, follow this arrow. You can see that the POH is defined as the negative logarithm of the OH minus ion concentration. And you can see that H plus and OH minus are interchangeable to one another as well, because they use H plus times OH minus is equal to 1 times 10 to the negative 14th, or the KW equation to go between. And then a really nice handy equation is that pH plus POH is equal to 14 down here, and it allows you to easily translate between those two. And so if you know one, you can find 3 other identifying factors about a particular solution. Other P scales also exist. there's a pKa and a pKb scale, and of course that just means that you're taking the negative logarithm of that Ka or of that Kb. So in 16.5, we talk about strong acids or bases, and we'll put this pH scale to use for them as well. In strong acids and strong bases, there's complete dissociation. For example, Hickel breaks up to give you H pluses and Cl minuses, and nothing else. There's none of this remaining anymore. And so whatever the concentration of HCl was, that equals the concentration of H plus. The same is true with strong bases. Whatever the concentration of KOH was, this equals the concentration of OH minus. And so if you're given a concentration of 0.1 molar for each of these, that's actually the concentration of H plus or OH minus, depending on which species you're talking about. So when you're asked to calculate the pH or the pOH or the H plus or the OH minus, use the concentration of HA or use the concentration of BOH, whatever the base is. And those will give you the H plus or the OH minus ion concentration as long as they are strong. As long as they are strong. If they're a weak acid or base, wait till next video cast. Let's do a bunch of example problems using the pH square. Make sure you have your calculator out and you can follow along and you can try some of these. First of all, the example problem number 1 says calculate the H plus, the OH minus, and the pOH of HCl that has a pH of 2. I'm going to move this paper over, and then I'm going to put the pH square right out over here. I'm going to hold my calculator handy right here so you can see how I go along and do the calculations. So first thing is to note where you are on the pH square, right here. And then you realize that you've got to find all other 3 species in there. And the easy one to move to from pH is to pOH. And notice I can go from pH to pOH doing 14 minus the pH, because pH plus pOH equals 14. So 14 minus 2.5, that should give me 11.5 for my pOH. Just to make sure, because I made some mistakes the other day on I was helping some people on a Zoom call, and we ended up doing something like that, and I think I got an answer like 5. So I'll do them all in the calculator, even though they probably seem like I should be able to do them in my head. Next, let's go from pH to H plus. And so follow the arrow right here, and it says H plus is equal to 10 to the negative pH. And that comes from knowing that pH is equal to the negative logarithm of the H plus ion concentration. And so if you know this, how do you get to here? And you have to use the 10 to the x key on the calculator, because you do it to the base's power to find that. And it's going to be 10 to the negative power because there's a negative sign right here. And so in this case, I'll hit 10 to the x key, and I'll put in negative 2.5. And I get a H plus ion concentration of 0.00316, or the way that you usually write this is in scientific notation, 3.16 times 10 to the 123 negative third. To 2 sig figs, this would be 3.2 times 10 to the negative third. And then lastly, to go to the OH minus ion concentration, I have 2 choices. I could either go from here to here, or from pOH to OH minus. And since I did this direction already for pH to H plus, I'll do this equation here. And so H plus times OH minus is equal to 1 times 10 to the negative 14th. And since I know H plus, I can put that into this equation. And so I could take 1 times 10 to the negative 14th, and I could divide that by my answer right here. And I will get the OH minus concentration to be 3.16, or let's round it to 2 sig figs, 3.12 times 10 to the negative 12th. These, of course, would have molarity after them because they're a concentration. pH or pOH don't have units because they're an exponent, because they're the logarithm, and so they don't have units on them. One other example problem, let's calculate the pH, the pOH, the H plus from a solution of 0.05 molar BaOH2. I chose this one because it's tricky. When BaOH2 dissociates, which it does completely because remember this is a strong base, it gives you Ba plus 2 and 2 OH minuses. Notice this 2 right here. And so if they told you the concentration of BaOH2 is 0.05 molar, if I want to know the concentration of OH minus and then get myself onto the pH squared to find everything else, I need to multiply it by 2. So 2 times 0.05 is 0.1, which means my hydroxide ion concentration is equal to 0.10 molar. From there, I can choose which way I want to go to find the other pieces on the pH square. And let's do the negative logarithm of 0.1, and then that should give us the pOH. And if you're a savvy math student, you can say, oh, this is the same as the negative log of 1 times 10 to the negative first. And you could split that up into 2 logs, and it's the same as the negative log of 1 plus the negative log of 10 to the negative 1. The log of 1, of course, is 0, and the negative log of 10 to the negative first is just this exponent, and there's a minus sign here and a minus sign here, and so we should have a pOH of 1. To make sure I did that right, let's do it on the calculator. So negative log of my answer is equal to 1. So my pOH in this case is equal to 1. This makes the pH super easy to find because the pH and the pOH always have to add up to 14, so that means the pH is 13. And then if I want to find the H plus ion concentration, remember that's going to be the 10 to the x key of whatever the pH is, so that means it's going to be 10 to the 13th power, or 1 times 10 to the 13th. But just to make sure that I did that correctly, let's type it in the calculator. 10 to the x key, and then, I'm sorry, it should be negative 13th. And then we'll put in negative 13, and we'll get 1 times 10 to the negative 13th, because remember pH is equal to the negative logarithm of the H plus ion concentration. And so if I know the pH is 13, I have to take 10 to the negative 13th power, and there's my H plus ion concentration for this strong base solution of barium hydroxide. Good luck with your pH calculations.